Hello and welcome back to another coding session with Mr. Jacob. Today we finally want to integrate resampling or resizing into our currently used dithering project. I guess in the end I will rename it because it will be some sort of image conversion and processing pipeline to have all the tools there for me to convert easily between images or photos that I have to a data structure that my e-paper picture frames can read. But today the main topic is resizing, and I want to implement Lanczos. I'm not sure how this is actually pronounced. I think I will say Lanczos, so Lanczos resampling. So please, if I don't pronounce it correctly, first of all, please tell me in the comments, and then please, I'm sorry for that if I say it wrong all the time. So essentially, what is Lanczos resampling? Lanczos resampling is essentially we have a one-dimensional signal which has been it has been sampled at a specific frequency, as you can see here, for example, and then we are actually we are actually trying to interpolate between the samples. So we want the values between the samples, and we want to essentially interpolate them. So we need this to resize an image, then of course in 2 dimensions, but we will take a look at the this in a second. We want to interpolate between those samples to make the image, for example, bigger. So if we make an image bigger by 2, for example, we always have a pixel in between which we need to somehow fill with data that we didn't have before. And Lanczos can there give us pixel values that are kind of a quite nice interpolation actually of the image. There are different other algorithms, like, for example, bicubic interpolation, or even bilinear interpolation and stuff like that. And usually today, often bicubic or Lanczos are used for image interpolation. I've actually never implemented Lanczos resampling before, but I've read a little bit about it. I've read this Wikipedia article beforehand, and I guess we can try to implement that. What we essentially need to implement for that is, for once, the Lanczos kernel, defined as L of x, which has a specific implementation here, which uses the sync function in it. We can take a look at sync in a second. And we then have kind of an interpolation formula when we are doing a convolution across all our different samples. Then we can actually use this sum formula here to create and calculate the points in between based on this Lanczos implementation or interpolation. And there is actually some neat information about the multidimensional interpolation. So what we need is 2 dimensions, as our picture has 2 dimensions. And this is essentially just multiplying the Lanczos kernel of the x value with the Lanczos kernel of the y value. So this is quite easy to do. I hope. We will see. We will see. So yeah, I guess let's try and integrate that into our project. So I had it open, I guess. Yeah. So here is our dithering project. So if I run the cargo here, we see that it generated these dithered PNGs. So let's quickly open that. That is what we implemented before. We implemented dithering, and then we cleaned up the whole thing a little bit. We have a lot less dependencies than we had before, because we are, in the last session, we created a C binding ourselves to STB image write, which was quite nice as well. And as you can see, there we have our dithered image. But now we want not only to be able to dither something, but to resize it as well. As I've said, I most likely will rename the project in the end. So let's go ahead and switch to our code editor here. And yeah, we are currently, this is our main RS, so there isn't much in there. We have splitted out the image handling, which is the reading and writing. We have splitted out the dithering, which is handled here. And now I guess what we need is something new. We need, I guess, something like resizing, resizing.rs. And then I guess we need to load that. So let's do that, and let's maybe create the calls already that we need here. So I guess for now we don't need to dither the image, but we want to do something like resized, or let's do two variants. Let's do a smaller one and let's do a larger one. So let's smaller would be, I guess, resize Lanczos or something like that. Is it actually written like that? That's not. There is a Z in between. Okay, so like that? Wait. Oh no, in the end there is an S. Okay, so yeah, I guess I will make that mistake a lot of times. So I guess we will do something like Lanczos resizing, and I guess we will put in the image there. Let's see. And yeah, I guess a new size, something like image.width divided by 4, for example. So image by height divided by 4. So let's make it a fourth of the image, or an eighth then actually, because we are doing it in 2 dimensions. Yeah, and I guess this can fail, so let's do that, and then let's do a bigger variant of that and simply multiply this by 2. Yeah, and then I guess we need to save the file, so let's do that. And let's give it the smaller one. And yeah, I guess for now we can simply hard code the output here, smaller.png, for example. And yeah, let's eliminate this context for now. And let's copy that and do the same thing to the bigger one. So bigger.png. And I guess this leaves us with implementing resize Lanczos. So I guess we can already import that here, resizing, resize Lanczos. So yeah, let's import that. And now let's switch over to resizing and let's try to implement that. So we need a pubfn, resize Lanczos. And I gave it the image as a reference to an image struct, and then I gave it the new width as a usize, I guess, and the new height as a usize as well, and it returns some sort of result with an image in it. Yeah, looks right to me. So I guess we need to import a couple of things here. So use anyhow result. And I guess we need use create image, I guess. And then we in the end need to return some sort of image. So let's quickly do a to-do here so that the compiler isn't screaming at us all the time. Okay, so now let's see, how does this actually work? This Lanczos filtering, by the way, I'm sorry for this bright Wikipedia. I have actually an extension which can make it darker, but it unfortunately doesn't work on... Oh, it works better than it did a couple of seconds ago. Okay, then I will have turned it on, I guess. It didn't invert those functions when I checked it before starting the recording. So yeah. So now this is darker as well a little bit. Okay, so I guess what we first need to implement are those kernels here, this Lanczos kernel, like the function here, I guess. So maybe we should simply implement that, or let's, yeah, where do we actually start? I guess we can start with that because we will need it in the end. So because this is part, yeah, it's part of the convolution formula. So yeah, I guess let's just implement this. So it is actually if a -8, an a is a sort of a parameter, I guess. This is now okay. So so yeah, this is actually the Lanczos kernel that we are actually moving along the function, or later on in a two-dimensional version. So this will actually then interpolate the values in between, and you can actually, it's parameterized, so you can actually change this value of a to make it behave a little bit different. We can actually play around with that, I guess. Yeah, so I guess we need to implement that. So yeah, I guess let's do that as a function, Lanczos, and it takes just an x. So this is an x, and this is actually, I guess, a floating point. Yeah. I guess those are all floating points in this domain. So, and we have this parameter a. Yeah, I guess this will be a floating point as well. Not sure, and it will return a floating point. So let's see. If it's between -a and a, so if x is, or yeah, if -a is smaller than x, or x is smaller than a, then we want sinc of x times sinc of x divided sinc of x over a. So I guess we need to implement the sinc function then. So it's sinc of x times sinc of x over a. Yeah, and otherwise we want to return 0 as an F64, I guess. And now it complains, of course, it doesn't know what sinc is. Yeah, I understand that. So let's implement that, as I guess. It takes an x as well, and it returns an F64 as well. So let's see how this sinc function actually looks like. Okay, sinc of x is actually sine of x over x. Okay, yeah, that's quite simple, I guess. So we can do that. For x does not equal 0. So what is it actually when it is 0? So unnormalized, often called sampling, digital signal processing. Yeah, commonly defined for x does not equal 0. Okay, in digital signal the normalized sinc function is commonly defined for, okay, maybe we want this one. I guess that is the one that we had here. Let me quickly open that as well before. This is actually, I guess, this one, which has been inputted there. So maybe we want this one. I'm not sure. We will see. In either case, the value at x equals 0 is defined by the limiting value. Okay, so for sinc 0, we want simply to return 1, if I understand correctly. So we need the same thing here as well. So if x, yeah, but it's floating point. So we want the absolute, and we want to see that if it's smaller than the epsilon value of the F64 floating point, then we simply want to return 1, and otherwise we want to return this, I guess. Yeah. Okay, so now we have our sinc function, and it's complaining because I didn't put an F64 there. Okay, now we have our Lanczos function and we have our sinc function. So I guess we can start implementing the resize Lanczos algorithm. So let's think about that. I guess we will need to, what we want to do is we want to calculate the new image. So we essentially first of all need to create something like new image, I guess, which is a vec of colors. So color from RGBA, yeah, we just create empty color, a black color there. So, and yeah, we need to import that, of course. And I guess what the size we want there is new width times new height. Yeah. Okay. And now we need to, I guess we need to iterate the new pixels. So what we want to do is like something like new y in 0 to new height. Yeah. And for an x in 0 to new width, we want to iterate over all new pixels. And now we need to somehow use Lanczos to calculate the corresponding color at that position based on the old image. Okay, so let's see. That is the sync function Lanczos. So I guess that is the interpolation formula. Yeah. For one-dimensional convolution. Yeah, we need to implement this one here. So what we need here somewhere is something like fn Lanczos 2D, and it takes an f, and it takes y, and it takes the a, and it returns an f64. Yeah, it should return one value, I guess. And this is defined as simply as Lanczos of x with a times Lanczos of y with a. So that's actually the definition for a two-dimensional convolution kernel. Okay, so now that we have that, let's see. We have this convolution defined here somewhere. So given a one-dimensional signal, okay, we will treat it two-dimensional, but that's fine. We know how to do that. So given a one-dimensional signal with the samples Si for integer values of I, the value Sx interpolated at an arbitrary real argument, and that is essentially what we want. X is obtained by the discrete convolution of those samples with the Lanczos kernel. So what we actually want is we need this real argument. So what we need actually is a fractional number representing what our current new pixel would be with regards to the old image. Yeah. So what we actually want to do here is something like original x or original y equals, and I guess we need then new y times, and then the proportion between the old and the new one. So I guess image dot height divided, and we need to do that as in floating point space. So we actually need to do all of that in floating point space. So divided by new height, is that correct? Is that the correct order? Let me quickly think about that. So if the old image, the original image, is for example 100 pixels high, and the new one is 200 pixels high, then the factor should actually be 0.5. Yeah, so that makes sense because the factor needs to be a half, because we need to interpolate pixels in between the pixels that we have actually. Yeah, so then for example, the 10th pixel in a row maps to the 5th pixel in the original image, and the 20th pixel maps to the 10th. Yeah, it makes sense because we need to space it out more. Okay, so this is right, and we need to do the same thing then for x. So and I guess then we can actually put this one there because it doesn't need to be recalculated for every row, but for every column, but only for the rows. Okay, makes sense. Yeah. Okay. So now we have this fractional real this real argument here, which is fractional thingy. Okay. And now we need to convolve. Okay, so now we are going actually for integer values of I. So given a one-dimensional signal, samples Si for integer value of I. So the value as x interpolated as an arbitrary and so on. So Si is actually the real pixel. I see. Okay. So oh, that is why the x is floored here, because the x is currently the x here is the fractional part. So we floor it, and then okay, I see. So we need to iterate from the floor of x minus a plus 1 to the floor of x plus a. Yeah, I guess we can do that. So let's do that. So let's call that IY. We started always with the rows. Yeah. So we need to do this two-dimensionally then. We need to do this for x and for y. So for our IY in no, not 0. It starts at OY dot floor minus a plus 1. So plus 1 F64. Let's do that like this. And then I guess we tell it to do it as a usize. And then we need to go to OY dot floor plus a. And we want to iterate that as a usize as well. Is that correct? Do we want it to? Yeah, I guess we want it to, because it is an integer. Yeah, for an integer value of I. Yeah. Okay. So as usize. And then I guess we need to do more or less the same thing, but for x, because we need to convolve there two-dimensionally. So x. So this would be OX floor, and this would be OX floor, and yeah. Okay, let's reformat quickly. And now we need to calculate, this part. So SI is the sample for integer values. So it's essentially the original sample at position I. So, but this could actually be, cannot find value A in this scope. Oh, interesting. Yeah, we don't, I guess we want to pass that maybe, so that we can play around with that. I don't know if there is a fixed number for that, which one uses, but we will see. Okay, so what we actually want to check, do we need to check if this could actually create a pixel value outside of the image, doesn't it? Because I guess if we are at, for example, if this value is 0, then this would actually be negative, and that is something that, that can't actually happen because we are casting it as a usize, which might not be the best idea, because actually it can be negative, and then we have some very strange behavior there, I guess. So let's check that. Let's see if IY is less than 0, or IY is bigger than image.height, which is the original height. Yeah. Or ix is less than 0, or ix is bigger than image.width. Then we simply want to skip that point because we are outside of the image, so we can't actually calculate that. Yeah, okay, let's do as isize. Okay, let's see. So then we want to continue. Otherwise, we are doing this here. So we are taking the sample at, in our case now, as SXY, so from the real value there, yeah. And we are actually multiplying that with the, okay, so I guess we need to do that for the colors. So I guess what we need to do is something like new R, which is, let mute R. I'm not 100% sure which type this needs. Let's see in a second. I think this will need to be a floating point because we are summing things up. Yeah, we are summing things up, and I guess we are summing things up in the floating point domain. So that makes absolute sense. So we now have values for all our new colors outside of this convolution loop. So what we actually can do, and I guess we should start them at 0. We can actually then do it like, let's do it like that. So they are actually equal 0 F64 semicolon. So yeah, so now they automatically have the type. Okay, so we now have new RGB values there. So what we need to do is now we need to calculate new R. Should plus equal, because it's a sum, yeah, the real pixel value, so the one that is of integer value I. So essentially the sample at this position. So the sample at the original position, but without the fractional part. So essentially we need this, we kind of need this float OX value quite a lot of times. Maybe we could store it somewhere else. But for now, let's simply do something like wait, is that, no, that is, we already have that value. That actually is, yeah, that actually is our, that is the IX and IY we calculated. Okay, so what we actually want to do here now is we want to take from the original image the pixel IY times image width plus IX. Yeah, okay, and we want the red channel of that. And this does not work because, yeah, because now we make them use sizes again. But we can actually do that because we checked that they are not negative. So this is actually fine. Maybe there is a better way to do this. We will see. But first of all, I just want to make it work somehow. So, and yeah, cannot add. Yeah, okay, that makes sense. So we want that as an F64 because we will multiply it in a second with, so that is actually our SY here. That is our SY. So now what we need to do is we need the two-dimensional Lanczos thingy here, X minus Y. So what we actually want is we want to multiply this with Lanczos. Didn't we define a 2D Lanczos? Yeah, with a 2D Lanczos. And what we want to put in there is the real I, so not the one that we floored here, but the real one actually. Yeah, so the original X, original Y, and the A. And it was original, it is x minus I. So we take this one and we subtract ix, and here we subtract iy. And I guess this should not work because this is the wrong, yeah, as f64, as f60. Oh, so we are essentially only passing the fractional part into the Lanczos. Okay, that makes sense. Yeah, that actually makes a lot of sense. So we are only putting the fractional part in there. So I guess what we could do there is maybe something like, isn't there something like fract, which should only give us the fractional part then? Turns the fractional part of self. Yeah, I guess we can, but maybe we shouldn't do that now because we are simply going along with the Wikipedia article and implementing that. We can do that later on, I guess. So yeah, okay. So now we have that for R, and now we need to do that for G. So we want here the G value, and I guess we could factor this one out. Yeah, why not? So let wait. So we are weighting those pixels during iteration by this Lanczos term here, I guess. So I guess we can then do simply here multiplied by weight, and this can go, and we have B. But I guess in the end, if we are summing this up, we need to go back in the end to our usual value there. So once we are outside of this loop, then again, we now have here our new RG and B values. But how do we actually, where A is the filter size parameter, and yeah, the bounds of the sum are such that the kernel is 0 outside of them. Yeah, that's okay. So continuous everywhere, continuous is the Lanczos kernel is 0 at every integer argument x, except at x0 where it has the value 1. Okay, yeah. Therefore, the reconstructed signal exactly interpolates the given samples. Okay. Multidimensional interpolation. So samples for integer interpolated at an arbitrary real argument is obtained by the convolution of the samples kernel, where A is the filter size. So I guess what we need to do is to kind of... So intuitively, I would do something like, I would actually want to have something like, because it is a weighted sum. So what we actually need to do is we need to get the sum weight or something like that. I guess we'll see. Maybe this will look horribly wrong, but so sum weights plus equals, and it needs to be mutable, of course. Sum weights would then be, I guess, the weight here. We would put the weight there, and then in the end we would kind of divide all our new values by this sum. So to normalize it again. Yeah, I guess. So that would then actually be new image, I called it, I guess. Yeah. And new y times new width, new width plus new x. And then the R value of that would actually be new R divided by some weights. And I guess we want to round that, I guess. So we can round that. And then I guess we want to clamp it between 0 and 255, because I guess it could actually be... not sure if it can be less than. Actually, I guess it can't be less than 0, but it could be more than 255. if the interpolated value has some sort of brightness that goes outside of this range. And then we want that as a U8. Is that correct? Might be. New image. What is the problem here? Cannot mutate. Yeah. So mutable new image. There we go. And then I guess we need to do the same thing for G, RG. And I guess we will see very shortly if I've done things horribly wrong or if this works. So actually now, I guess we are kind of finished. We can now return an image. Oh, we need to wrap it in. Okay, okay. So we can return an image with data, which is new image, with a width, which is new width, and with a height, which is new height, I guess. Okay. Yeah, maybe we have just implemented Lanczos resize. Let's take a look. So I guess what we need to change is I added a parameter here, this A value. Is there actually something in the article about the A? Lanczos kernels for the cases A, 2, and 3. Note that. Okay, so is there something here in this of the sink? Each interpolated value is weighted as a weighted sum of 2A consecutive input. Yeah. Thus, by varying and so on, 2A. According to Jim Blin, the Lanczos kernel with A3 keeps low frequencies and projects high frequencies better than any achievable filter we've seen so far. So I guess we will start with a 3 there. So this needs to be an F64 and yeah, so I guess, crossing my fingers, let's do and try this. Okay, it's running, it's doing things. It's taking quite some time. And we went somewhere out of bounds. So where did we actually go out of bounds? At resizing 45. So let's see. Resizing, or wait, no, not resize RS, resizing RS. No, not color. What the hell? Resizing RS. Line 45. There we are. So wait, this one got out of, oh, no, wait. This one got out of bounds? IY as usize times image width as usize plus IX as usize. So how can this actually go out of bounds if I checked before IY smaller 0 or IY bigger image high, bigger equal? The same thing. I always kind of fuck up. So let's try that again. So it's going for quite some time, but I guess we are creating kind of a really big image there. The base image was actually quite big there already. So maybe we now have a bigger image there, which is 13 megabytes, okay, and a smaller one, which is half a megabyte. So open the smaller one. Okay, this doesn't look completely bad. So, oops, what did I do there? So let's zoom in a little. That actually looks quite okay. So this is of course now not dithered. It's just resized. We could dither it before or after, just how we want. I guess we should dither it after, because otherwise we would introduce new colors. Okay, let's open the bigger one. I guess we might have done something right. Okay, this actually looks okay. So did this really work on the first try? That would be kind of amazing. So let's make it, maybe let's do the following. Let's make this thing a lot smaller. And then let's make the smaller one bigger again. So back to its original size, something like that. So first we shrink it a lot, and then we make it bigger again. Let's see what happens there. Come on. Yeah, I guess there is optimization potential there, even though the system is now very much doing all of its thing by recording. But I guess I have done something wrong there. It can't take that long. Oh shit! Yeah, I see what I've done wrong there. I've just created an absolutely enormous image by taking the size of the original image times 8 and not the size of the smaller one times 8. Okay, let's see again. This shouldn't actually take that long. Yeah, okay. So let's take a look at the smaller one. Okay, this actually really looks kind of fine because you can see the pixels, but the overall structure is still intact. So this is actually something I would expect from this kind of resizing. Okay, so how does this look now if I do something like the larger one? Bigger one? So this should actually be, yeah, it is of course smoothed out a lot, but that's essentially what the Lanczos filter does. Yeah, it smooths out from the really small thingy here to the big one. So you have to keep in mind that this smaller one actually, can I tell it to actual size? Yeah, that this is actually only the original size now of this image. We made it a lot smaller, so it needs to be blown up somehow. And yeah, okay, this looks actually really, really nice. I guess we did it. I guess we created Lanczos resizing. Yeah, it's really nice. So actually the real size of this is actually like this. And there you can actually see some sort of artifacts there because we need to somewhat blow up this image a lot. But it's still quite nice actually. Yeah, so I guess we did it. I guess we have just, let me move this over there. We've just implemented Lanczos resizing. Yeah, I actually really like that. I guess I will refactor image dither a little to, as I've said, provide some sort of kind of processing pipeline for us in the future. Yeah, please leave me some comments if you have any ideas to how to go on with that, or if you would like to have a video about this refactoring or not. And then I guess we can go on further in the next videos once I've determined how to further process this stuff. I guess the next thing there would be something like grayscale conversion, for example, and then maybe having the proper tooling to export this into a binary format for the e-paper or stuff like that. But I guess we are kind of close. We could even maybe implement another different resizing algorithms now, like for example by linear resizing or by cubic resizing, which work in a... Essentially, they all work in the same way, but do different mathematical convolutions and calculations there. But Lanczos is, as far as I know, one of the most established. Lanczos or bicubic is the one to go there, which most image editing programs go today. So yeah, thanks for joining me again. I wouldn't have thought that this would work out so nicely and in the first try of actually implementing that, but in the end the Wikipedia article was quite good and had all the information, and in the end even something like this, which might look a little bit intimidating at first, isn't that hard to implement then, because it's only the mathematical way of describing some for loops that we have now here. We have we simply have implemented this in a couple of for loops and calculated that, and yeah, it works out. So I guess thank you for joining me, and I hope you had fun. Please give me a thumbs up if you liked it. leave me a comment, push the subscribe button, hit the bell. You know the usual drill to make YouTube advertise this more so that other people might see it as well. And yeah, I hope to see you in the next one. Bye.